The first video from chapter 13 is about calculating rotational inertia or moment of inertia, which is chapter 13-2 in the textbook. Okay, so back in chapter 12, at the very end of chapter 12, we defined moment of inertia. So moment of inertia was the measure of rotational inertia, how difficult it is to change an object's rotation. And we found it depends on the mass and exactly where the mass is relative to the axis of rotation. However, we didn't really calculate it for anything. So to calculate it for a single particle or particles, so what you do is the moment of inertia is defined as the mass of the particle times r squared, where r is the distance from the particle to the axis of rotation. And if you have multiple particles, well, you just add up all the moments of inertia for the individual particles. So you take the sum of the individual mass times for each mass is going to have the distance to the axis of rotation. Right, so R, capital R here is the perpendicular distance from the particle to the axis of rotation. Now, if you have an extended object, so a rod or a sphere or whatever it is, so the thing to do is to imagine dividing up into infinitesimal little bits of mass. So you take your extended object, say your pencil or your rod or whatever, you slice it up into 1,000,000 little infinitesimal bits, and then you treat each one of those bits as a particle. So this sum of, sum m sub I r sub I squared, well, now if these little m sub i's become infinitesimally small, so this is actually now a Riemann sum, so this turns into an integral. So to calculate the integral, we need to do the integral r squared dm. Now, in practice, usually what you end up doing is you look up for common objects like hoops and spheres and cylinders and whatnot. Somebody has already done this integral, so you look it up in a table. Now, one other useful bit of information is something called the parallel axis theorem. So if you look at the table on the previous slide, the moments of inertia for those are always calculated relative for an axis going through the center of mass. Now, and it turns out there's this thing called the parallel axis theorem that says if you know the moment of inertia through the center of mass, to get the moment of inertia through some other axis parallel to that, you just take the total mass of the object, capital M, times h squared, where h is the distance from the axis through the center of mass to the new axis.